You ever stop and think about the absolute paradox at the heart of our digital world? We build these incredibly powerful technologies on components so small you can't even imagine them. And we do it inside factories that are some of the biggest, most complex buildings humans have ever made. So let's dive into how that's even possible. And just to set the stage, get this. The smartphone in your pocket, it's got about 62 different microchips inside. And across all those chips, you're looking at something like 90 times billion transistors. That's more than 10 for every single person on the planet, all crammed into something you can hold in your hand. It's just wild. So that leads us to the big question for this whole explainer. How in the world do we do it? How do we build billions of things we can't see inside buildings the size of a small town? Well, we're going to find out. We're going to zoom all the way in and then all the way back out. Okay. First things first, we're going to go deep inside a finished product, the central processing unit, or CPU, the brain of any modern computer. A CPU isn't just one thing. It's more like a super dense three-dimensional city. You've got different neighborhoods, like here you can see the 24 cores, the memory controller, a graphics processor. Then below all that, you have this crazy network of 17 layers of metal wires. These are called interconnects, and you can think of them like the city's freeways and streets, zipping data around. And all of it, this entire metropolis, is built on a foundation of billions and billions of tiny transistors at the very bottom. And that foundation, that's where things just get completely mind-bending. We're talking about a scale that our brains just aren't built to understand. So just how small are we talking? Well, the space between transistors can be just 57 nanometers. To put that in perspective, a mitochondrion, the little powerhouse inside our cells, is almost 10 times bigger. A tiny speck of dust, nearly 50 times bigger. And a single human hair is over 1,000 times wider. We are literally engineering structures that are way, way smaller than the basic building blocks of life. Okay, so we've seen what we're building. Now for the really big question. How is it even possible to manufacture something with that kind of insane precision? Well, it all comes down to a really, really complicated recipe. This is probably the best analogy for chip making I've ever heard. It's like baking a cake that's 80 layers tall. The recipe has 940 steps, and the whole thing takes 3 months to bake. But here's the kicker. If any single step, any temperature, any measurement is off by just 1%, the entire cake is ruined. You have to throw it out. There are no small mistakes. But here's the secret. That incredibly complex 3-month process is really just a simple repeating loop. First, you add a new layer of some material onto a silicon wafer. Second, you use a special process with light called photolithography to make a perfect stencil. Third, you etch away all the stuff you don't need. And fourth, you clean and check your work. Then, you just do it all over again, layer after layer after layer. We've seen the nanoscopic recipe. Now, let's zoom out and look at the colossal kitchen where this cake gets baked, the semiconductor fabrication plant, or as everyone calls it, the fab. This is where it all goes down. We're talking about a clean room that could cover 8 football fields, and it's packed with hundreds of machines. Some are the size of a van, others are as big as a bus, and each one costs millions of dollars. Some cost over 150 million, and each one does just 1 or 2 of those 940 steps in the recipe. What's really amazing is that no human ever touches the product. The silicon wafers, they travel in these sealed pods holding 25 at a time. They're called FOUPs. And these pods just zip around the factory on this overhead robotic railway, kind of like a super clean miniature subway system. Robotic arms then pull each wafer out, put it in a machine, take it out, and send it on its way. That whole journey takes 3 months, and a single fab can be juggling 50,000 of these wafers at once. Now, to make sense of the hundreds of machines, you can really just sort them into 6 basic jobs. You've got the photolithography tools for making the stencil. You've got deposition tools for adding material and etchers for removing it. You've got ion implanters that actually modify the silicon itself. And of course, a whole army of tools just for cleaning and inspecting. Every machine has its part to play in that big repeating cycle. Out of all those tools, photolithography is without a doubt the most important and by far the most expensive. It's basically a super, super advanced copy machine. It shines powerful UV light through a stencil called a photomask, and a massive set of lenses shrinks that pattern down and prints it perfectly onto the wafer.
And to build just one type of CPU, you have to do this over and over with 80 different unique photomasks.
So, now that we've been inside the chip and inside the factory, let's put it all together. Let's follow the complete journey from a blank piece of silicon to a finished CPU ready to go in a computer. It all starts right here with a single, perfectly pure 300mm wide wafer of silicon. Before it even goes into the fab for its 3-month journey, it's worth about $100. But after 3 months and 1,000 different steps, that same wafer comes out covered in hundreds of finished CPU dies. And its value? It has exploded to around $100,000. By weight, that makes it literally 10 times more valuable than solid gold. So let's trace the whole path. It begins with a giant crystal of pure silicon being grown and then sliced into these thin wafers. After that 3-month marathon in the fab, every single chip on the wafer gets tested. Now, they're not all perfect. The ones that have tiny flaws get sorted or binned into different categories. This is actually why we have different models, like an Intel Core i9, i7, or i5. They could have all come from the same wafer. They just have different levels of perfection. Then, the good chips are cut out, put into their protective packaging, and boom, they're ready for a motherboard. So, the real takeaway here is pretty simple, but it's huge. Everything we think of as modern life, our phones, the internet, AI, even medicine, it all stands on the foundation of this one impossibly precise, ridiculously complex manufacturing process. It's the engine that runs pretty much everything. And that leads us to a final, really fascinating question. For decades, getting better meant getting smaller. But we are getting incredibly close to the fundamental physical limits. We're talking about the size of actual atoms. So if this process is the engine that powers our world, what happens when we can't make that engine any more powerful?